A related concept to gradient is divergence. So we did this already. Originally, actually, I wanted to cover like these two in one video, but I thought maybe it will be a longer video because I tried not to keep any of these video more than 1 hour. But anyway, I split it into two videos, but they are very related concept. In the previous video, like on the previous video, I showed you how this gradient could be useful in optimization problem. In this video, I will show you like how these two guys, like gradient and divergence, could be very useful in describing flow, for example, in porous media or contaminant or heat transport or things like that. These types of equation, yeah. And similarly, we'll do FE exam problem and some basic problem. Okay, so let's just get started. What do we have here? So we have a function. It giving like a vector field. Remember, like what we did before. What we did before, they were like we were giving like a scalar function. But this here, like you see this bold. Remember, I told you that's a vector function. So what would the vector function look like? So that's here I cannot do bold here, but I can just put this arrow here. This indicate like this is a vector, yeah, of x, y, z, and that will be f1 the I direction plus f2 in the j hat plus f2k hat. Yeah. Uh, so this is a vector function. Now remember this guy here. Let me just remind you of this guy. Remember what's this guy? This is like the Nabla operator, and this is like the gradient. So this is dy over dx partial. Sorry, not d. Partial over partial y, partial over partial z. Yeah, that's so and by definition, this is a vector, yeah, because this is like another way of writing a vector, yeah. So I can write this guy also, you know, as a vector form, like similar with ijk. That's the same here. So basically, and similarly, I could just write this guy in this form, yeah. So I can like just write my f in this form also, yeah, like f1, f2, and f3. You see here, it's like same guys, yeah. Okay, now this is the dot product of this guy. So this is a vector and this is a vector. The dot product of this guy and this y, like this is a vector, this is a vector. You know what we will get? We'll get a scalar. So if this is partial x partial y partial z, yeah, and then f1, f2, f3, yeah. If you like that will, like, so this is a vector, this guy is a vector, that will give you a scalar. So this is, you can multiply this guy by this guy, so you're multiplying two vectors, that will give you like f1 partial x plus f2 partial y plus f that's like, yeah, f partial z, yeah. So basically you get something like this, yeah. Okay. So this I got like a scalar function. So here I have a vector function. This guy is a vector dot product of a vector. I get like a scalar function. Okay. So now remember in the previous, like gradient is point to the steepest ascent, yeah, or the path of the steepest ascent. Divergence basically tells you indicate like a positive divergence, like if this guy, yeah, if I evaluated this guy at like any point and became positive, this indicating like a source. If I evaluated this guy at any point and it's like negative, that indicate like a sink. Example of source like recharge, for example. Example of a sink pumping. Yeah, that would be an example of a sink. Okay. Uh, uh, so recharge, like you have an aquifer and you recharge it, like your water is infiltrating it and making your water table go up. But again, this is the problems are easy. So like again, this if you got one of these guys in your FE exam, that is kind of like a bonus or easy points to get. Why? Because here I'm giving you like calculate the diversion of the following vector function. So diversion, yes, one thing I forgot to tell you, but diversion, it has different notation. One notation is like gradient dot product of your function, or simply diversion of your function. So this divergence of your function, these two are equivalent, yeah. So this gradient dot product the function or the diversion of the function. So let's so this is my vector function, and what is divergence of the function? What is the the actually, you know, my handwriting is not good, but I think one thing I can do, I can actually type. Yeah, let's try typing. So like if you copy this guy, for example, and you paste this guy here, it doesn't matter. Here, I can type, yeah. So I can say like ver divergence of a function. Yeah. So that's a vector function, yeah. And then that's at a point, yeah. So the divergence of this function, I mean, that's not difficult, remember? So that is like this guy, and that will give me a scalar. So that would be parture f1 over x plus parture f2 over parture y plus parture f3 over z. Yeah, so that would that's the general rule. Remember, this guy is this guy and this guy is this guy. You just get a scalar. Yeah, this is 3. So this is my f1. So that would be with respect to x. So that I will get z. Yeah, that's a scalar. So this will go away, and x here, this will be like a constant plus parture f2 with respect to y. So this will go away, so that I will get like x square plus x square. Parture f3 with respect to z. I don't have z here, so this is a constant, this is a constant, so that's like 0. So basically, it turned out to be like z plus x square, yeah? So now I want to evaluate like the divergence at a point, yeah? So at like this point, like divergence at a point, let's assume like here's the point like -1, 1, and -1. So that would be equal to, so z, that's like -1. So here that would be -1 plus x square. X square is -2. So that's like -2 square. So that will basically give me like 4 -1. That will give me 3. Yeah. So diversion. Oh, I already have it here. I think I have it confused. Yeah, that's this guy here. Yeah, sorry. So that is the diversion of the function. That is like the diversion of the point. And now I'm asking you, is this like a source or a sink term? Like And this is positive. So remember, positive diversion indicate like a source. So this is like a source. Okay. Uh, while negative diversion will indicate a sink. And since this is like positive number, so this point, yeah, like at this point is this function like is like there's a source at this point. So this is the source. So see, like these problems are trivial to solve. They are not difficult to solve. I mean, the concept might be challenging a little bit to understand. They come with experience, but like the problem, like when you see this in your exam or in your homework, that should be easy problem. You just get them, yeah. Okay, so here is like a practice problem. Try to do it. Yeah. I think is it the same one that you have here, or I give you a different one? No, actually, oh, I give you this. No, it's a different one. Yeah, it's just like a different one with a different point. So try to solve it. So you find the diversion of a function, diversion at a point, and then if it's positive, then it's a source. If it's negative, then that is a sink. So try to solve it, and after you solve it, check your answer. So that's like the answer. If I solved this correctly, and you got something here, this seems positive. Yeah, I didn't need to calculate it. So that is uh, uh, since the point source indicating region where air is spreading out, source versus a negative converging. Yeah. Uh, so here I just put like it context to the problem, like which I didn't do here, like so you will understand more. Like so in this problem I just put a context to it, and this is your homework problem, similar stuff. I made it a little bit more challenging here so that you can practice what you did in uh, what do you say in in previous lesson. Remember, like about uh, oh, here also you see this a little bit more challenging, so you can practice what you did uh, in in, uh, in the previous lesson. Yeah, so basically, like here. Remember, I mean, let me do it. So, I mean, you can read the problem. It's telling you fluid expanding at a point suggesting turbulence and blah blah blah. So you can read this, but here, like you will find the divergence of H and the divergence of H. Remember that will be like F1 partial X plus F2 partial Y plus F3 partial Z. Yeah. So that's something like this. So if you look here at this guy, uh, remember that would be like, this is like your x or u or whatever. So len x, that's 1 over x. So that would be 1 over x plus 1. Yeah. Multiplied by the derivative of this function. And the derivative of this function is 1. So you basically will not get anything. Here, like this guy is easy. You can do it. This is guys is straightforward. Uh, Here I am basically doing this with respect partial f3 with respect to z. So this is just a constant, yeah, and this is my z. So I will get like 1 over x plus y, and here this one you can easily do it. And then once you just substitute your point here, then you will get something, and then you will get like a number. So like you see, if this number is positive, then this will be like a source. Yeah, if this number is negative, then that will be like a sink. And so a sink means like, for example, like the fluid will uh, be compressing at this point. So sink means that the fluid is compressing versus source would be as the fluid is expanding, something like this. Okay. How we are doing in time? Not bad. Okay. Uh, okay, so here let's just look at this guy just to see this, like I told you, I will show you these concepts, like the gradient concept and the divergent concept with one of the equation that's commonly used to like it's a form of Laplace equation, yeah. Uh, so product of a vector with, I'm just like repeating what I said again. Product of a vector with a scalar is a vector. So I have like this gradient operation, that's like a vector, yeah. So again, that would be del, that's like partial x over partial I plus partial y over partial z plus partial z over partial k. This is all, yeah. So this is like gradient, that's like a vector guy. And I have my scalar function, yeah, my scalar function, my scalar function. So that would be like the head at x, y, z at different parts, like in my aquifer. So the gradient, yeah, the gradient, yeah, the gradient of the head, yeah, which is like this, like parture head, yeah. So the gradient of the head, that would be what? That would be parture h, parture x in the I direction, plus parture h, parture y in the j direction. You have to put this here, plus parture h over parture z in the k direction, yeah. So you got something that looks like this. Remember, I can also express it in another notation. So that's okay. I can remember, I can say this is like parture h over parture. I can express it like parture, not delta, parture h over parture x, parture h over parture y, parture h over parture z. Yeah, I can also express it in this form here. Yeah. So this guy is a vector. Yeah. So this is like a vector because this is like a vector here. Okay. So this guy is a vector. Yeah. This guy is a vector. This guy is a scalar. Okay. This is a vector. Now the product of two vector is a scalar. So I have the product of two vector is scalar. So I have another, yeah. The product of like two vector is a scalar. So now I have this guy here, or like this guy here, like the gradient of h. Now what is the divergence of delta h? Yeah. So here, this guy is a vector. Yeah. This guy is a vector. Yeah. This guy is here. This guy is here. Yeah. And this guy is here. So the gradient, the divergence of like the head gradient. So this is the head gradient, and this is the divergence of the head gradient. That actually will give you like a scalar function, not a vector function, because let me just write this to you like like how you do it. Yeah, so this is a vector. Yeah, so this is basically parture. Oh, let me just do it. So this is a vector, parture over parture x, like this guy here, parture over parture y, parture over parture z. Yeah, and this is like dot product with this guy here, parture h over parture x, parture h over parture y, and parture h over parture z. Yeah, so this will give me what, like, so these two, yeah, this will give me like a scalar function. So I can write it again here, like the divergence of the hydraulic gradient will give me parture 2h over parture x squared, just multiply this guy, parture h over parture y squared, partial h over partial x squared. Okay, this is actually like a form of Laplace equation. Laplace equation did something like this, but here was the temperature, and this will can also describe the flow, contaminant transport and flow. Okay, so here we have actually this is our this is a form of our groundwater modeling equation, and let me see what I have here. Okay, so I have more details that I can show you here. Yeah. Okay, so now let me just explain like this what we called here. So this is the diversion. Yeah. So this is my flow field. So I have something entering here and like something entering here, and then I have something leaving here, something leaving here, something leaving here. In that case, yeah, so this is like our, so that's my volume, my controlled volume, and this is what's entering and this is what's leaving. In that case, diversion is not equal to zero. Why diversion is not equal to zero? Because that, so this is a flow field and this is like, I'm just like plotting the diversion. So like see this gray line here is the flow field. This basically shows you the diversion, like what's like entering flux and leaving flux. And diversion here is not zero because what is exiting the system is more than what is entering the system. So that's why you don't get uh, so the flux is going out is more than the flux that are coming in, basically what you have here. Versus like you look at this guy here, this is like my flow field. Yeah. So like I have something that's exiting here, but what is exiting or like what is entering, like the diversion, like if you look at just what's entering here and what's like exiting here and what's entering here is what's entering here is the same. So there's no sources or sinks here. Yeah. So you don't have any source or sink at like this point, so your diversion basically is equal to zero. And when your diversion is equal to zero, means that like you are at steady state. Yeah, like basically like your mass inflow is equal to the mass outflow, and that basically like that is like steady state. Yeah, so you are in uh, you are like a steady state, or like you've reached it, like you are at equilibrium. Okay, so at steady state, like when the diversion is equal to zero, so like in that case, what do I have here? I have like my diversion here. Sorry, so that's my diversion. So that is the diversion again. So is equal to zero. Diversion is equal to zero means that like I'm at a steady state. So diversion is equal to zero, which is in this case what's coming in equal to what's going out, like mass in is equal to mass out. We will do a lot of these practice when we get to the conservation of mass. Basically, this means that partial uh, h over partial x squared plus partial over partial x squared plus partial over partial x squared, that's like equal to zero because my diversion is equal to zero. Yeah, and basically that shows how like h, like within your system, like within your system, that basically shows you the gradient of h, like how h is changing within your system. Like that describe like is this is like the gradient of the gradient, the rate of a change of the rate of a change, basically. Yeah, because this guy is basically like, I can write him differently. I can write him, this is like partial over partial x of partial x over partial x. Yeah, this, this is just like another way of writing this. This is like the rate of a change of like the rate of a change. So that's a gradient and that's a gradient of the gradient. Yeah, and I will. So this means that, I mean, you don't really need to know all these details. I hope I'm not confusing you, but this means that like let's say here I'm here, and like let's say I'm here and like another guy is here. So let's say this guy is like hot and this is guy is cold and I should be like somewhere in between, yeah? So that what the gradient will tell you, like if this is hot and this is cold, this would be somewhere in between, yeah? But what this guy will tell you is that if this guy like is the rate like the state of this guy will not depend on the value of this guy or the value of this guy, but the rate of a change of this guy and the rate of a change of this guy. So if this guy went up, and let's say this guy went the same way down, that guy will stay in place, regardless of their value, because that's the rate of a change of the rate of a change. Let's say this guy went up like this guy went up like this, and this guy will go up also, because it depends not on its value, but the rate of a change of this guy. I hope I'm not confusing you. You don't need really to understand all this, but uh, uh, I mean, this is at a transient state. Let's see how we are doing in time. I don't want to keep this very long. Uh, Not bad. I mean, let's do it. Okay. So at the transient condition, so this is at steady state. Yeah. And in a transient condition, the head will be changing in time. So that's not a steady state. So like your head here, it will be like changing in time. So like this diversion will not be zero and your head will be changing in time. So like you can get something like, so you basically get this. I mean, this is groundwater stuff. You don't need to. So delta H over delta T. So now your head is changing in time. That would be equal to partial X plus partial y plus partial h over partial z. So basically, this tells you the change in head in time depend on how your head is changing in space. That would be like in the transient condition. If I want to write this like in this, I mean, I could also write like partial h, yeah, is equal to something like this. Yeah, you can also. That's basically That's that's what we have here, yeah. And that will be this is like this guy, yeah. Okay, something like this. Now let me show you like another case. Again, if you don't understand much of these things, that's fine. Let me show you like another case where, see here in that case, like I'm assuming K, which is my hydraulic conductivity. Do I have a photo for this? Oh, okay, here we go. So yeah, I have all these cases here. So this is like the steady state case. Let me try to copy it and paste it. Okay. That's like the steady state case. Yeah. And this is like a transient case. Okay. So this is transient. This is a steady state. So that's basically equation that describe how head, like the hydraulic head, change within something that can look like this. Or now let's do another case like steady state transient condition for heterogeneous hydraulic conductivity. So we assume that the hydraulic conductivity which controls the flow is heterogeneous because subsurface is not the same thing. It's like heterogeneous, yeah. So in that case, this K will not be constant. K will be actually would be changing with X, yeah. K will be changing with Y, and K will be changing with Z, yeah. So it's not going to be constant because it's like a heterogeneous aquifer. So in that case, I can just like, I know this is the rate of a change, yeah, of K, of what? Of K partial h over partial x. So now you see k is changing with x. So like at different location, k will be different, yeah? Plus partial y of k partial h over partial y plus partial over partial z. have a typo here. Sorry. Okay, partial over partial. Sorry, partial over partial. Z of partial key partial H over partial Z. That will be equal to partial H over partial T. Yeah. Okay, which you can also write it. So this is a gradient. Remember, like this is a gradient vector, and this is the. So basically, you can write it like so as the divergence of your gradient vector multiplied by the hydraulic conductivity, which could be scalar or could be like a tensor or whatever. In that case, it will be a tensor. Like in that case, this is like a scalar, this is like a tensor, like because it changes in x, y, z, and then also in direction. So that could be something like so now if you see something like this, you know what does this mean. This is like is a vector function, and this is a vector function, and this if you multiply this vector functions, that will give you a scalar function that looks something like this. Yeah, give you a scalar functions that look something like this. Okay, so that's all for this lesson. How we are doing in time, not bad. Okay.